Alright, so here we have a very healthy equation, but do not get scared with the length of the equation. Let me tell you one thing with my experience. The lengthier the equation is, simpler it is going to be. Why? Because a lot of data will be provided in that, right? You can use that to solve the equation, and let's see what this statement says. At the start of an experiment, one end of a U-tube of 6 mm glass tube is immersed in concentrated ammonia solution and the other end in concentrated hydrochloric acid, right? So you have a U-tube and one end is immersed in ammonia, NH3, and the other end is immersed in HCl, right? Okay, so let me just represent that pictorially so it becomes more clear to you. Let's say this is ammonia, right? And this is your HCl, okay? Further, the equation says, at the point in the tube where vapor of ammonia and hydrochloric acid meet, white cloud is formed, and that white cloud is because of the formation of ammonium chloride, right? Ammonia is going to move from this direction, HCl in this direction, and at some point, let's call this point A, this point as B. A is the point from where ammonia is going to start, B is the point from where HCl is going to start. So they are going to meet in between at point C, let's suppose, and that point is going to be like in the middle. No, not exactly. Why? Because ammonia and HCl, they have different molar mass and their rate of diffusion is going to be different. So if I just see that way, ammonia is like 14 plus 3, 17 gram per mole, and HCl is like 36.5 gram per mole. So HCl is higher in molar mass, so HCl is going to move slowly. So I can say that point C will be somewhere close to HCl, somewhere close to point B. Okay, fine. The equation says, at what fraction of the distance along the tube from the ammonia solution the white cloud is formed? Okay, so basically they're asking you the distance AC divided by the total distance, that is AC plus CB, right? This is what fraction that you have to calculate. Okay, fine. So let's apply the concept of diffusion and effusion. So the rate of diffusion of a gas, that depends on the area of cross section, but that is same in this case. It depends on the temperature. It is not talked about, so we are going to assume it to be same. It also depends upon the time of travel. That is obviously same. Why? Because both the gases will be released at the same time, right? So the rate in this case is going to depend only on the molar mass. So if you talk about the molar mass of ammonia, yeah. So this is going to be the relation. Rate is inversely proportional to under root of molar mass, and similarly rate of HCl will be inversely proportional to molar mass of HCl. If I just take the ratio rate of ammonia by rate of HCl, this is going to be like molar mass of HCl divided by molar mass of ammonia. If I just put the values, HCl is like 36.5 and ammonia is like 17. So this is going to be 36.5 by 17. So if I just divide 17 into 2 is like 34. So this is going to be like 26.5. So this is going to be somewhere around under root 2.2. Fine. Okay, let's leave this here as it is. The other factor, how you can calculate the rate of ammonia in HCl, is the distance that is traveled by the gas upon the time taken. And the time for which both the gases are traveling is exactly the same, right? So if I just write rate of ammonia in terms of the distance that is traveled by ammonia, if I just look at the diagram once more, the distance traveled by ammonia is AC, right? So AC divided by time. Similarly, if I just calculate the rate of HCl, this is going to be CB divided by time. If I just take the ratio again, RNH3 by RHCl is going to be AC by T whole divided by CB by T. T gets cancelled. T is the time period of travel. That is same for both of them. So I'm left with AC by CB, which is nothing but root 2.2, right? RNH3 by RHCl. This is what we have calculated. If I solve this further, AC by CB root 2.2 is going to be like what? Root 2 is 1.41. So root 2.2 will be close to like 1.45. Let's take it approximately. So 1.45. Okay. But we have to calculate AC by total distance. So what do I do is, let's do one thing. Let me add 1 on both the sides. Right? So if I just do that, no, let's do one thing. Let me take a reciprocal of this. If I just reciprocate this, CB by AC, and then I'm going to add 1 on both the sides, this will be 1 upon 1.45. If I just add 1 on both the sides, CB by, okay, CB plus AC by AC is going to be 1 plus 1.45, taking LCM on both the sides, 1.45. CB plus AC, okay, this is the total distance. And if I just divide, if I again reciprocate it, this will be like AC upon AC plus CB is equal to 1.45 upon 2.45. Exactly, this is the fraction that I was looking for, the distance traveled by ammonia upon the total distance. This was the fraction. So I have to like solve this. 145 by 245. If I just cancel this with 5, 145, 150 is 30. 29, 250 is 50, 49. Okay. 29 by 45. This is what 49, sorry. 29 by 49. This is what I need to calculate. So if I just put it 0, 0, 29, 45, 49, 490. Okay. So this is going to be like 5, 9, 5, 45. 50 into 5 is like 250. So 49 into 5 will be 245. Okay. 545, 90, 45, 45. Now if I just solve this further, 450, 490, this is going to be at 9, of course. So 490, 49, 81, and 9, 4, 36, 8, 36 and 8, 44. So this is going to be 0.59, and this is like what? 10, 1, 41, 50. 9, 90, 49, 0.2. 0.592 is going to be approximately my answer. 0.592 is your final answer. Let's look for the options. 0.682. No. Further, far away. 0.534 is pretty close. Let's see. 0.466 is again no, far away. 0.595. What we have calculated is 0.592. Very close to 0.595. Yes, D for Delhi is going to be the right answer to this question. And with that, we conclude this beautiful question. Thank you. Okay, so here we have a question based on the reaction intermediate, and let's see what does the question demands. The question says, which of the following is correct regarding a carboanion intermediate? Okay, fine. So let's see how can we form carbanion. One of the best ways to form a carbanion is by using a Grignard reagent. So let's talk about that. Let's say we have CH3 MgBr, right? This is like methyl magnesium bromide, and this is an organometallic bond in between the carbon and the Mg, right? So magnesium, because this is an electropositive metal, obviously the bond is going to break towards the carbon, and what we are going to form is CH3 minus methyl carbanion plus MgBr plus, right? So let's further talk about this CH3. If I just draw the structure, this is going to look like CH3 with one lone pair with a negative charge, right? Okay, fine. And let's read the options now. It is sp3 hybridized. Okay, see, you have 3 sigma bonds over here and one lone pair, right? One lone pair. So that means, and lone pair is obviously counted in hybridization. So lone pair is basically present in a hybrid orbital, right? So you have 3 sigma, 1 lone pair. That means it is going to be like sp3 hybridized. So yes, this statement is true. This could be the probable answer. Let's look for another options. It is formed due to homolytic cleavage. Homolytic. No. What we have seen here is a heterolytic cleavage. Homolytic cleavage leads to formation of free radicals, right? We know this, okay? So, no, this is not correct. This is an incorrect statement. It is an electron deficient species. Oh, something with a lone pair, something with a negative charge is highly electron a rich species, right? So this is also incorrect. This is not electron deficient. CH3 minus or in general carbon ions are electron rich species. Okay, none of the above is obviously not correct. So yes, A for Australia is going to be the right answer to this question. And with that, we close this question. Thank you. Okay, so here we have a question based on the inductive effect, and let's see what does the question demands. In which CC bond of this molecule, okay, this is like chlorobutane, is the inductive effect expected to be the least? And you have in the options C2 and C3, C2 and C1, C3 and C4, none of the above. Okay, so they are basically asking you that pair of carbon-carbon bond where the effect of the Cl, this electronegative Cl, this minus I showing group, minus I group is going to be the least, right? The effect is least. Okay, okay. So as we know, inductive effect is a distance dependent effect. As you move further away from the group, which is showing the impact, which is the minus I or the plus I group, as you move further away from the group, the impact is going to minimize. And in general, after third or fourth carbon, we do not see the effect of any electron withdrawing or electron donating group, right? So the maximum impact is going to be on this carbon, then it is going to decrease on this carbon. If you talk about Cl, this is like del minus, here it will be del plus, right? Partial positive charge. If you move further, this will be partial of partial positive. You move further, partial positive, and moving further, obviously the impact is going to be negligible. So the right answer will be in between C3 and C4, the impact of electronegative chlorine, the dislocation, the partial charges because of dislocation of sigma electron is going to be minimum in between C3 and C4. Look for the option. Yes, I hope you can see the right answer. Thank you. Yeah, so here we have a question based on the magnetic properties of ions. Let's see what the question says. Which of the following is a paramagnetic substance? Okay. And in the options, you have 4 ions. So how are you going to decide the paramagnetic behavior, right? And that is decided by the number of unpaired electrons present inside an ion or an atom, right? So for that, we have to write the electronic configuration. So let's start magnesium. Magnesium is like 12 atomic number, and let's write for the atom first, then we'll derive the electronic configuration for the ion by removing the electron, right? Okay, so magnesium atom is like 1s2, 2s2, 2p6, 3s2. Perfect. And because this is like Mg2 plus, so we are moving from 12 electrons to 10 electron, and those 2 electrons will be these 3s electron that are going to be removed. So if I just remove this, this becomes 3s0, and what I see is all the inner electrons are paired. So 0 unpaired electron. So can I say this is going to be diamagnetic? Make sense? Okay. Moving forward, copper plus 1. Okay, copper is something which has the special electronic configuration. So atomic number is 29. Let's write it for 29 first. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Although 29 should be like 4s2 3d9, but because the fully filled electronic configuration are more stable, there is an electronic transition from 4s to 3d. Okay. Now, when you are removing the outermost electron, it should be 4s1. So let me just write it in this fashion: 3d10, 4s1. You are moving from 29 to 28, 29 to 28. You have to remove one electron, and that will be 4s1, right? So if you just remove it, it becomes 4s0. And what we observe is in the whole configuration, there is no unpaired electron. 0 unpaired electron, again going to be diamagnetic. Okay, moving further. Mn7 plus, manganese is like 25 atomic number. So if I just write for manganese, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, right? And Mn plus 7. So from 25, you are going to move to 18. and 18 is the electronic configuration of noble metal, and there all the electrons are paired. Without doing anything, I just know there is going to be 0 unpaired electron. But still, let's do it. So let me first change 3d5, 4s2, removing 7 electron, 2 from 4s, 5 from 3d. So this will become 3d0, 4s0. Again, 0 unpaired electron, going to be diamagnetic. So yes, obviously the answer is option D, but we have to verify this. This is titanium. So scandium titanium, it is going to be 22. So if I just write 1s2, 2s2, 2b6, 3s2, 3b6, 4s2 and 3d2. Right, so you just have to write in that fashion shell wise. So this will be like 3d2, 4s2. Now we are going to remove 2 electron from 4s and this will become 4s0. Yes, look at 3d. So if I just draw it over here, D has 5 orbitals, 1, 2, 3, 4. So this is going to be like 2 electrons, and one by one you have 2 unpaired electrons, the beautiful unpaired electrons. So yes, titanium 2 plus is going to be paramagnetic in nature. So yes, D for Delhi or D for Denmark is going to be the right answer to this question. And with that, the visuals for this question is over. Thank you. Alright, so here we have a question based on inductive effect, and let's see how we're going to solve this all together. The statement says, in which of the following cases incorrect, okay, direction of inductive effect is R shown. Okay. So let's talk about the inductive effect. It is of basically 2 types, the plus I effect and the minus I effect. If you talk about plus I effect, this is like something which is electron donating group. Okay, plus I effect is shown by with a group which is electron donating in nature, right? For examples, you have alkyls, you have CH2 minus ion and many more, right? If you talk about minus I, this is a property which is shown by electron withdrawing group, something which is highly electronegative, something which is electron deficient, something which has a positive charge, right? Okay. So based on that, if it is electron donating group, then the electron density will be pushed towards the carbon chain, and if something is electron withdrawing group, then the electron density or the shared pair of sigma electron, that will be pushed towards the electron withdrawing group, right? Okay, so if you just go by that way, option A, you have NO group, nitroso, right? So nitrogen is electronegative, oxygen is of course electronegative, so this whole group is electronegative, so it is going to pull that shared pair of electron towards itself, right? So the arrow should be in this direction, but this is reverse. This is exactly reverse. This is an incorrect notation to show inductive effect. So yes, this is incorrect. Moving on to further option B. If I just see C triple bond N, okay, C triple bond N is like what? Cyanide, okay, cyano. So carbon here is sp hybridized. So percentage of S character is like 50%. That is pretty high, okay. So yes, this is highly electronegative, and nitrogen is of course an electronegative element. So yes, again this group is electron withdrawing. So the electron density should be towards the group. The notation should be towards the group, and that is what is shown here. This is perfectly fine. B is correct. Option C. Okay. So you have C double bond O. Oxygen is electronegative. You have again one more oxygen here. Oxygen is an electronegative element, so it is electron withdrawing in nature. So the direction of shared pair of electron, direction of dislocation of sigma electron towards the oxygen will be fine, right? So yes, this is towards the oxygen. This is also going towards the carbonyl group CO. So yes, this is also correct. Fine, perfect. But we are looking for the incorrect representation. Fine. Moving on to option D, you have CH3, CH2, MgBr. Okay, magnesium. This is like a Grignard reagent, right? Ethyl MgBr, and you're going to read about this further. This is an organometallic compound, right? This CMg bond. Mg is a metal, of course. It is an electropositive in nature. So obviously, it is not going to pull the electron towards itself, right? Magnesium is a metal which does not like much electron density around itself, right? So this is going to be towards the carbon atom, right? So this notation is perfectly fine. Yes, this is true. It should be towards the carbon chain, towards this carbon chain, right? So yes, this is also correct, but we are looking for the incorrect option. So only incorrect representation is option A. A for Australia is going to be the right answer to this question. And with that, we conclude this question. Thank you.